I'm gonna record. Was there any preference, Jordan, 4 or 5? Okay, so he's saying he's got an unstable connection. He'll probably watch it when he can. Okay, so I'm gonna, does anybody, this was on the differential equations assignment, 4 or 5. Anybody have a question on one of those two, or do you want me to tackle any one of those two? If not, I'm gonna pick number 4. Okay, hearing nothing there, I'm gonna pick number 4. And so we're gonna look at the following in which the differential equation is given to us. So it says it's a current in an RLC circuit, and it's described by I1 double prime plus 6 I1 prime plus 10 I1, and that's equal to 0. Also given are the initial conditions. The initial conditions are I1 of 0, which is equal to 1. Notice, and we haven't talked in great detail about this, right now we're doing I1 of 0, I1 prime at 0. Why are we not doing 0 minus? So I1 prime of 0 is equal to, problem 4 is equal to 3. Why are we not doing these values at 0 minus? Any idea? Anybody?
Because right now there's no switch, so
exactly. Yeah, that's great. That's awesome. There's no switch, so it doesn't matter. We don't have to look at some condition when a switch is thrown and all of a sudden something in the circuit changes. This is the circuit. Nothing is changing in the circuit, and so we just know these conditions at t is equal to 0, and then we know that it behaves according to this differential equation right here. Okay, this is a homogeneous equation. It's set equal to 0. It's a homogeneous equation. There's only a homogeneous response. So for this, we're going to establish the characteristic equation is s squared plus 6s plus 10 is equal to 0. So we get to factor this. And if we factor this, I think what we'll get, if I do this correctly, is s plus 3 plus j, s plus 3 minus j. I think I've factored that correctly, is equal to 0. So we know that s1 and 2 are conjugate, and they are equal to minus 3 plus or minus j. Plus or minus, as a reminder, 1j, just as a reminder that 1 is the imaginary part. So we know that the homogeneous response for this is in category 3, and that response looks like the following. So it's an I1, so it's I1 homogeneous, but because there is only a homogeneous response, it's going to be the I1, the total response. So it's equal to K1 sine of this one right over here, the one that multiplies the imaginary part, sine of 1t. Most of us don't write sine of 1t, we just write sine of t, but I'm putting it in there so you can see it, plus K2 cosine of 1t. Again, most of us would not write it that way. And all of that multiplies e to the minus 3t. This minus 3 goes in that exponent, and that 1 goes there and there. So that is our homogeneous response, and because there is only a homogeneous response, it is the complete solution. So now I have the initial conditions. So I'm going to need I1 prime, and this is among the ugliest derivatives that we have to take. Anytime we're dealing with the sines and cosines, multiplied by an exponential to find that derivative, we always have to use the quotient rule. So in using the quotient rule, it's the derivative of the first, beautiful, cosine of t, with my K1 out in front, and then minus K2 sine of t, that's the derivative of the first, times the second, times e to the minus 3t, plus the first, K1 sine of t, plus K2 cosine of t, times the derivative of the second, times minus 3 e to the minus 3t. This minus 3 is a multiplier that's going to appear here and here. So I'm just going to put this together, and the way I'm going to put it together is all of these are either sine of t times e to the minus 3t or cosine of t times e to the minus 3t. So I'm going to look at the sine terms first. So here we go. The sine terms. This is the sine term. Here's the coefficient, minus k2. And over here, the coefficient is minus 3k1. Minus 3k1 minus k2. That multiplies sine of t. And it's going to have an e to the minus 3t afterwards. So hold on to that. There's the e to the minus 3t afterwards. And now the same thing for the cosine. So the cosine term is, there's a k1 on the cosine. And over here, there is a minus 3k2, minus 3k2. And all of that multiplies cosine of t, and all of that times e to the minus 3t. So that's I1 prime. So now we're looking here at these two equations to use our initial conditions. I1 at 0. So for I1 of 0, I'm looking here at this equation up top, I1, and I evaluate this side that I'm just underlining. I evaluate it when t is equal to 0. This is always going to happen. Sine of 0 is 0. So this term is not going to end up playing a role in that initial condition. It'll always be just the cosine term. So we know the initial condition given to us is 1. But now, from the analysis up here on this side, I'm going to get k2 times cosine of 0. Cosine of 0 is 1. So I have k2. And that k2 is going to multiply this exponential evaluated at 0. E to the 0 is also 1. So the beauty of this is I immediately have a value for k2. k2 equals 1. That's awesome. Now I do the same thing in the second equation, and I'm going to evaluate this. This is I1 prime. So I1 prime up top here is at 0. I1 prime at 0 is equal to, on this side over here, it's 3 from the top. And now on the right-hand side, it's this evaluated when t is equal to 0. Again, the sine term is going to give us 0. So it's going to be k1 minus 3k2, and then e to the minus 3t is times 1. So I have k1 minus 3k2. But we know what k1 is. k1 is equal to, here's our k1. k1 is equal to 1. So this is equal to 1 minus 3k2. So what I'm going to do is I'm going to bring the 1 over to the other side. I'm going to subtract 1 from both sides. I'll get 2 is equal to minus 3k2. And therefore, k2 is equal to minus 2/3. So we have our value of k1 and k2, and we're just going to substitute it into the solution for the equation. Here we go.
I think for that second one, you were supposed to solve for k1 instead of k2.
Was it k1? Thank you, thank you, thank you, thank you. Erase all of that. I'm going to erase it. Pretend you didn't see any of that. So all the way back to here. I substituted in for k2. Thank you so much. k1 minus 3 times 1. So now I'm going to add the 3 to both sides. And when I do, I end up with 6 is equal to k1. Thank you so much for that. I so appreciate you following along and helping out, because these things are being recorded and then you're going to have them later on. And if I confuse you now, you'll be even confused later on. So put my k1 there. So k1 is 6. So now we're going to substitute. k1 is 6. k2 is 1. Let's substitute them in. It's k1. So it's k1 sine of t plus k2 cosine of t. All of that, remember, multiplies e to the minus 3t. Let's put those values in. I1 equals k1, 6 sine of t, plus k2, plus 1. I'm not going to write the number 1 in there, but here it is, I will. 1 cosine of t. Obviously, 1 times cosine of t is cosine of t, and you're all sharp enough to know that. Group that together, all multiplied by e to the minus 3t. because this is a current, and I quoted that in the problem, a current, blah, 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 we can put the unit in as amps. So normally we don't just use the initial conditions to solve directly for K1 and K2. We wait for the forced response to be added in there. But in this case, there was no forced response. So the total solution that we had was just the same as the homogeneous solution. Okay, Jordan, is that good for you? Doesn't matter, he can't really see much, it looks like. Okay, so just for the heck of it, he mentioned 4 and or 5. I'm going to do 5 with you to continue to give us work in this particular area. I've given you a lot of homework problems this week, so I want to help you with a lot of them. So let's also look at number 5. So 5 is, it's a voltage, and the voltage is defined by V double prime plus 4V prime plus 3V is equal to 6. This is going to be one of our nicer situations because we have a constant forcing function. V of 0 is equal to 8, and V prime of 0 is equal to 2. Okay, so this time there is a forced response because I have this 6 over here and I'm not 0. So there's a forced response, there's a homogeneous response. We always start with the homogeneous response. Here we go. S squared plus 4S plus 3, and I don't know how this prime got here, but boom, get rid of that. 3V. V double prime, V prime, V. S squared plus 4S plus 3 is equal to 0. So factoring this, we end up with S plus 3 times S plus 1 is equal to 0. And you can see that S1 and S2 are equal to -1 and -3. Therefore, the homogeneous response, V homogeneous, is equal to K1 e to the minus t plus K2 e to the minus 3t. Okay, done with the homogeneous response. That's awesome. That's quick. That's easy. I love it. Now let's go to the forced response. So we know that our typical guess is going to be VF is A. It's a constant because this is a constant. But I have to make sure that A is not one of the terms up here in the homogeneous response. It is not, and so that guess is legitimate. It's a good guess. So VF prime is equal to 0. VF double prime is equal to 0. This is going to be really easy. We're going to substitute those into the differential equation, reminding you of the differential equation. V double prime plus 4V prime plus 3V is equal to 6. So we're going to substitute in. Here we go. 0, that's that one, plus 4 times 0, that's that one, plus 3 times A, that's this one, is equal to 6. 3A equals 6, A is equal to 2, and therefore V forced is equal to A, which is 2. So now I have V forced, V homogeneous. Now we're going to tie that all together and put that into our complete response. Here we go. The complete response is the forced response plus the homogeneous response. And so that's equal to 2 plus K1 e to the minus t plus K2 e to the minus 3t. Just a reminder, we have the initial conditions are, for this particular problem, it's V0 is equal to 8 and V prime at 0 is equal to 2. All right, whoop, put that right there. Slide that up. Okay, we have V, we need V prime. V prime equals, derivative of 2 is 0. Don't think I need to write it there, but I will. 0 minus K1 e to the minus t minus 3 K2 e to the minus 3t. You should be noticing the derivatives we see on a daily basis are the same darn derivatives. Derivatives of exponential functions, derivative of sine and cosine functions, derivatives of constants, derivative of t squared. They're the same sorts of functions every time. So it's not like we need to know 48,000 different derivatives. The only derivatives we've been using are the ones that we sort of boxed up and showed you. Okay, let's take v at 0. From here, v at 0 is equal to 8. There it is. It's 8. From here, when t is equal to 0, 2 plus k2. V prime at 0. From here, it's equal to 2. From here, it's equal to 0 minus k1 minus 3k2. Let's rewrite these over here. k1 plus k2 equals 8 minus 2, 6. Minus k1 minus 3k2 is equal to 2. No need to use Kramer's rule. It's too easy. We'll avoid that. We'll just add them. K's cancel when we add. Minus 2k2 is equal to 8. Therefore, k2 is equal to minus 4. Having that, let's substitute back into here. And so we have k1 plus a minus 4 is equal to 6. So we're just going to add 4 to both sides. Therefore, k1 is equal to 10. I have k1 and I have k2. We're ready for the complete solution. So the complete solution is v is equal to 2 plus k1, 10 e to the minus t, plus k2 minus 4 e to the minus 3t. This is a voltage. It is in volts. Okay, so we've done a lot of those problems in that assignment. There is one, you should note, there is one that is going to be excitation at a natural frequency. Be aware of that. What should happen is if you don't recognize that it's excitation at a natural frequency, you're going to make your guess. Then when you put your guess in, you're going to get 0 is equal to something. Like 0 is equal to 10 e to the minus 6t, for example. And 0 is not equal to 10 e to the minus 6t, so you know something is wrong. What's wrong is your guess. Comments or questions on those two problems or anything else that we've done so far? Okay, if there are no questions on that, what I would like to do is I would like to look at 1 or 2 more problems that are on the circuits that I gave you. I gave you 6 circuits. We looked at one of them. I think Jack asked to do 5 yesterday. If I remember correctly, we did number 5. Anybody feel free to pick any one other problem that's on there. 1, 2, 3, 4, or 6. Let's do number 1. I'll pick one of them. I'm going to do number 1. And the reason I'm going to do number 1 is because I'm going to show you what happens when we don't choose the variables that I suggested make it easier. There are variables that make it easier, and I could do that on this circuit. I'm not going to. So instead, what I'm going to do is I'm going to show you what we do when we don't actually choose the variables that are easier, and we follow along with the mesh or the nodal analysis methods that we normally use. So we're going to look at problem number 1. This is on the second order circuits. Assignment that I've handed you. So the circuit looks like the following. It's minus. There's my current. There's current I. 5. And I have a 1 Henry inductor, and then on a 1/6 farad capacitor. Okay, that's our circuit, and our source is 26 cosine of 3t. And this says find I if I of 0 is equal to 2 and V of 0 is equal to 6. Okay. So here's what I'm going to do. This is the series RLC circuit. It's problem number 1. It could potentially be the hardest one depending upon how you tackle this problem. So here's what I'm going to do. I'm going to just go right around this loop here. And I'm going to write my equation. In fact, let's treat it like going around this loop. I'm not even going to call it a loop. It's a mesh current. So we're going to write this as a mesh equation. So around this loop, we have the following. Minus 26 cosine of 3t plus 5i plus 1 I prime. And now I want the voltage across the capacitor. And it's been a long time since we've looked at this, but I want this voltage across the capacitor, which is V, but I don't want to write it as V. This needs to be in terms of my mesh current. So I is the current, the only current that goes through the capacitor. And so you might remember that we had an equation that looks like the following. There are multiple ways to write it. So let's just this aside right over here to remember. For a capacitor, I equals 1 over C V, not I. V equals 1 over C, the integral from minus infinity to time t of I d tau, which we could also write the following way, equals 1 over C, the integral from 0 to t of I d tau plus V at 0. So which of these two, this one or this one, do you think I should use in the equation, and why? Which of the two forms? I could use either form. Which of the two forms, and why would you use it?
The second one.
Good. The second one works really well. Why would you use it? By the way, they both work, but if we don't use the second one, we'll have to do something different in order to get the second initial condition that we really need. So the second one works real well. And the reason it works real well is because we know information about this right here. So let's use it. What we don't know is we don't know what's going on from 0 to t. So 1 over C, C is 1/6. So 1 over 1/6, remember 1 divided by 1/6 is just 6. So this is going to be 6 integral of I, that integral is from 0 to time t, of I d tau plus V at 0. And we know what V at 0 is, but I'm going to put it in V at 0 right now. So that is equal to 0 when we sum those up. Just a reminder, V at 0, it's given to us. Here it is up here. I'll circle that for you up there. See that? It's equal to 6. So that's 6. Okay. Now, we haven't dealt with equations like this in this course. This is called an integro-differential equation. Integro-differential equation, because there's an integral and there's a derivative in there, both, and they are on the same variable. They're on the variable I. So here's what we're going to do. We're just going to differentiate this equation. That differentiation is going to get rid of this integral. Now, again, I mentioned this before, you're not experts on taking derivatives of integrals, but because that t is up here, we're going to have this derivative of this integral is going to be I, and it's going to be I multiplied by the derivative of t, the derivative of the upper limit minus the derivative of the lower limit. And I know you don't know this, you're not supposed to, but the derivative of a constant is always 0 and the derivative of t is 1. And so that's why this whole derivative of this integral gives us I. That's why that happens. Let me erase that. You don't need to see that. So here we go. The derivative of the first term. The 3 is going to come out front. I'll leave it out front. Negative 3 times negative 26 times the sine of 3t plus 5i prime. Derivative of I is I prime. Plus 1 times I prime and derivative I double prime. I'll leave the 1 off of there. Plus that 6 stays there. The derivative of all the rest of that is just I. It's exactly what you expect, but you're really not sure why. I just want you to think of this. The integral from 0 to 7 of I d tau is a number, and the derivative of a number is 0. The reason this derivative of this integral is I is because it's not a number. It's a function of t. It's a function of t, okay? Now, derivative of v of 0. Well, v of 0 is 6. It's a constant value. So that derivative is 0. Okay? The derivative of v of 0 is not v prime at 0. V of 0 is a number. Okay, clean this up. I double prime plus 5. 5i prime plus 6i equals, bring it all over to the other side. Those two negatives cancel, bring it to the other side. It's going to be a positive. I'm going to leave it 3 times 26. I know how to multiply them. I'm leaving them that way for a reason. Times 3t, and that all has a negative sign in front of it. Okay, there's our differential equation. That, believe it or not, is the hardest part of the problem. The rest is cumbersome. The rest is cumbersome. So while we're here, I'm going to pause right here, and I'm going to, before I solve this, so let's just put a box around this. What I'm going to do is I'm going to show you why this equation that we wrote, why we like writing it in this form. So I'm going to take this equation, and I'm going to do the following. I'm going to evaluate this equation at t is equal to 0. So I want you to see what goes on when I evaluate that equation at t is equal to 0. So here's what we have when we evaluate at t is equal to 0. Minus 26 cosine of 0 plus 5i of 0 plus I prime at 0 plus 6 times the integral from 0 to 0 of I d tau plus v of 0. Okay, I have all of that, and all of that must be equal to 0. Somebody look at this and tell me what the integral from 0 to 0 is. The integral of any function from 0 to 0. Just remember what an integral is. Here's a function. It's the area under the curve. But here's 0, and I want the area under the curve from 0 to 0. What's that area equal to?
0.
Beautiful. Now, we know this value, we know this value, and we know this value. And that's why we like writing the equations with the initial conditions in it, because it allows us to find the initial condition that we are after. That's where you're going to get your missing initial condition from. You're going to get that missing initial condition from one of the equations that you wrote. So cosine of 0 we know is equal to 1. So this is minus 26 plus 5 times I at 0. Scroll back up. I at 0, 2 plus I prime at 0 plus v at 0. We said v at 0 was equal to 6 plus 0 plus 6. All that must be equal to 0. So let's take this and this and that and bring it all to the other side. I prime at 0 is equal to, this is negative 26 plus 10 is minus 16, plus 6 is minus 10, bring it to the other side, it's positive 10. So now we have I prime at 0 is equal to 10, and we know I at 0 given is equal to 6. Given. All right, so we're going to use that with this differential equation. Okay, get that differential equation in sight. Now what's the first thing that I do? We're going to solve the differential equation. First step.
Find the homogeneous part.
Excellent. And to find the homogeneous part, the first step in that.
Write the characteristic equation.
You're outstanding, Jack. Thank you so much. S squared plus 5s plus 6 is equal to 0. S plus 3, S plus 2 is equal to 0. I just want you to know in the real world, they don't all factor real nicely like this. I try hard to make them factor like this, but sometimes it's really difficult to conceive and design a circuit where they come out really nice. It's not always easy. S, 1, 2. So just deal with the numbers. They're just numbers. Minus 2, minus 3. So the homogeneous response is I homogeneous equals K1 e to the minus 2t plus K2 e to the minus 3t. I've done this all along. I don't know if you've noticed it. I've tried to stay pretty consistent. You don't have to do this. Always choose the smaller magnitude of these numbers. The smaller one gets the K1, and then the larger one gets the K2. That way I don't have to scroll back and forth and keep looking, oh, which one was K1, which one was K2, which one was K1, which one was K2. So I always put the K1 with the smaller one, and then the K2 with the larger one in magnitude. Okay, we have the homogeneous response, boxed out. With all these things of boxing out, all this work that we're doing. Now we need the forced response. So look at this function over here. That's the function, that's the forcing function. So what is my guess going to be? Guess is equal to?
A cos 3 of t plus b sine 3 of t.
Excellent. So guess I forced equals, he gave the cosine first, so I'll do that. A cosine, and it's going to be the same omega that's in there, right? See that 3? That's where the 3 is coming from. A cosine of 3t plus b sine of 3t. I'm going to prove to you today, just so you know, that this is equal to the square root of a squared plus b squared cosine of 3t minus tan inverse of b over a. And we'll show you that. It's a real nice identity. In other words, it's just a cosine. You put in a cosine, you get out a cosine, or you put in a sine, you get out a sine. It's just shifted in phase. That's it. Scaled in amplitude, shifted in phase. That's what happens. Let's focus on not that part. We're going to prove that later, so don't worry about that. We'll prove that later. Let's focus on what we have. I need to now take this and get the two derivatives. So I need IF prime, which is equal to, and what I generally like to do is I like to keep the order the same. I want all cosines first, all sines second. So this one here, when I take that derivative, is going to give me the cosine. So it's going to be 3b cosine of 3t, and then minus 3a sine of 3t. Then IF double prime, and do the same thing. The sine is going to give me the cosine. And so when I take that derivative, I'm going to get minus 9a times the cosine of 3t. And then I'm going to get minus 9b times the sine of 3t. And you should notice a very particular thing that happens all the time. The numbers always match. The shifting from positives to negatives always happen in the same location, so that the process looks almost eerily similar every single time we do this. Now, we need to take these three, and we need to substitute these three into the differential equation. So a reminder of our differential equation. Our differential equation looked like the following. I double prime plus 5 I prime plus 6I equals, and then I think we had, I'm going to have to double check this, minus 3 times 26 times, I think it was the cosine. I think it was the cosine of 3t, but I'm going to pull it up and double check, so hang on. No, sine of 3t. Sine of 3t. Did we do all that correctly? Yep, we took the cosine, took a derivative. It's the sine of 3t. Okay. Okay, here we go. Substituting in. I double prime, that goes there, that goes there, that goes there. I know they're big, but they're not ugly. They're fairly easy to deal with. Minus 9a cosine of 3t minus 9b sine of 3t plus 5 times 3b cosine of 3t minus 3a sine of 3t plus 6 times, easiest one, a cosine of 3t plus b sine of 3t. And all of that is equal to minus 3 times 26 times sine of 3t. Notice over here, plus 0 times cosine of 3t. There's no term over there. In this game, it is always match the coefficients. Match the coefficients. So on the left-hand side, I need to group all of my sine terms so I know what the coefficient is and all of my cosine terms. So let's start with the sine terms. I have minus 9b, and then I have this minus 3a gets multiplied by that 5, minus 15b, and then the last one is b times 6 plus 6b. So all of those
should be minus 15a.
minus 15a. Thank you, Jack. Again, so appreciate you guys. Minus 15a. And then it's plus 6b, correct? Plus 6b. Okay, and that multiplies sine of 3t. And then I'm adding to that the cosine term, get all the terms. The first one is minus 9a. And then I have 5 times 3b plus 15b. And then I have plus 6a. And that multiplies cosine of 3t. And that is equal to minus 3 times 26 times the sine of 3t. Don't forget, plus 0 cosine of 3t. If you need that as a reminder, put it in there. So this coefficient over here is equal to this coefficient here. This coefficient here is equal to this coefficient here. So let's assign those. So minus 9b, actually, let's clean it up right now. So I have minus 9b plus 6b, that's minus 3b, and I have minus 15a. Minus 15a minus 3b, and that must be equal to minus 3 times 26. For the second equation, we have minus 9a plus 6a. That's going to give us minus 3a, and then plus 15b. And you're always going to have this. These numbers match up. These numbers are negative of each other. That equals 0. So you should look for those things. That should always happen. Okay, I'm going to take both lines and divide by 3 or divide by -3. So on the first one, if I divide by -3, I get 5a plus b equals 26. And the second one, when I divide by 3, I get minus a, excuse me, plus, let's see, do I want to divide by negative? It doesn't matter. Yeah, let's divide by a negative. So let's make that a positive a, and that'll give me a minus 5b, and I want the minus in there right now. And that equals 0 divided by 5, divided by -3, 0. Okay, now I'm going to take this second line, and I'll take that second line, I'm going to multiply by 5. Multiply by 5 and add. When I multiply by 5, I end up with, not the second line. Gosh, Dennis, wake up. First line times 5. So when I multiply the first line times 5, I get 25a, and then I'm adding plus 1a, so that's going to give me 26a. And then here I get 5b minus a minus 5b. They cancel, it gets a 0. And then I multiply and I get 5 times 26. Sweet. So we end up with a is equal to 5. So a is equal to 5. Now let's plug that in here and get b. 5 minus 5 times b is equal to 0. That's easy to see. B equals 1. Okay, so our solution, all this hard work for the solution. So I equals, now I have to remember what Jack gave us. Jack gave us a times cosine. So a times cosine, 5 cosine of 3t plus b plus 1 sine of 3t. And then we have plus our k1 and our k2. Plus k1, and I can't remember my numbers, but I think it's e to the minus 2. Was it 2 and 3? Yep, e to the minus 2 and e to the minus 3t. k1, e to the minus 2t, plus k2, e to the minus 3t. So those values can now be solved for with our initial conditions. So we have the initial conditions, just a reminder of the initial conditions, which we boxed up. Initial conditions are right here. I prime is 10 and I at 0 is 6. There's 0 equals 6. I prime 0 equals 10. Okay, that means we need the derivative of this function, I prime. That is going to be equal to minus 15 cosine of 3t plus 3 sine of 3t minus 2k1 e to the minus 2t minus 3k2 e to the minus 3t. Great, there's the derivatives. Now, here we go.
The sine and cosines need to be flipped.
Thank you. I know how to take derivatives. I'm good at them. Beautifully done. Thank you. Again, can't thank you enough for this. Okay, so now we're going to substitute in these values. I at 0 equals, I at 0, 6. Now from the equation above, here's the cosine. Cosine of 0 is 1. 1 times 5, 5.
I of 0 is equal to 2 on the initial condition.
Is it 2?
Yeah, I think V of 0 was 6.
Did I copy that wrong? I wrote 6 here. Is it 2? 2. I'll make that correction. V at 0 is indeed 6. I at 0 is 2. Thank you, Jack. Connor, Jack, thank you for keeping me on the ball. So this number is 2. So 5 from this one, 0 from that, plus K1 from the next term, plus K2. You see this repetitive thing happening over and over again. I prime at 0 is equal to 10, and that is equal to 0, 3 times 1, 3, minus, actually, if I wrote 0 on the other one, let me write it here. 0 plus 3 minus 2K1 minus 3K2. Let's just rewrite these over here. K1 plus K2 equals minus 3. And minus 2K1 minus 3K2 is equal to 10 minus 3. 10 minus 3 is minus 7. 10 minus 3 is positive 7, sorry. Positive 7. Okay? So what I'm going to do is I'm going to take the top equation, multiply that by 2, and then add them. When I do, those will cancel. Multiply by 2 is 2K2 minus 3K2, that's minus K2. Times 2 is minus 6, plus 7 is equal to 1. Therefore, K2 equals minus 1. Take that, substitute back into that one. That seems pretty easy. K1 plus a minus 1 equals minus 3. That tells me that K1 equals minus 2. So there are all of our values. Put them all together. I equals 5 cosine of 3t plus sine of 3t plus K1. K1 is equal to minus 2. Minus 2 e to the minus 2t plus K2 minus 1 e to the minus 3t. This is the current. It is in amps. Kind of interesting that I tell you, and I tell you this from experience, not because of what I think. I tell you the hardest part of this problem for most of you is going to be right here. Just that work. Look at all this work that we did afterwards. Look at all of this work. All of that's just mathematics. The hardest part is getting the differential equation, believe it or not. And that really didn't take very long whatsoever. So we're at 12:53. So why don't we take a 5-minute break right now? We'll come back after the break. But before we go to break, are there any questions? Anybody have any questions on that analysis? Any questions at all on the process? So again, I didn't use the mixed mode method. I could have written one KVL equation, one KCL equation. I did not do that. Instead, I opted to write one equation I put the integral differential equation there. Sometimes when you do that, what can happen is you'll end up with a third order differential equation. Then you'll have to integrate that equation back down to get a second order differential equation. So I tend to stay away from that for the most part, but the series RLC circuit is a pretty easy one. And for that reason, I opted to write that equation because I didn't think it was going to be cumbersome. Okay, if there are no questions right now, I'll ask again when we come back. So you can either take a look at that, but in the meantime, take a good 5-minute break for yourself, and then we'll come back and we'll reconvene. I'm going to put our recording on pause. So we're going to pause our recording, and I'll see. Okay, I'm back. I hope you are too. So any questions on anything that we've gone over this morning, this afternoon, early this afternoon? Any questions about any of that? For those of you who are in the state of Arizona, you know that Governor Ducey made his declaration yesterday. He's declared us to be work from home, stay at home, et cetera, et cetera, et cetera. So I've been doing these lectures in my office. I'm not sure if I'm going to continue to come into the office and do them here. I've been working out of the office these past few days. But it might be a different feel. I'm a little concerned about it. We've got pretty good internet at our home, but I'm worried about the speed of it and whether or not things get a little clunky. So we'll see how things go over the next few days. Let's talk about the oral presentations. So the oral presentations, I was thinking we would do them this Friday. That's what I was thinking, but I'm open to pushing them off till next week. What's your opinion about that?
Yeah, I'd be happy to do them next week. I've got quite a few assignments due this week. Just
Okay, good.
that's okay with everyone else.
Yep. Enough said. That's good. We'll wait till next week, and we'll establish a time for when we're going to do those next week. Then. Okay. How are we feeling with regard to developing the differential equation from the circuit? I know we've only done like 3 of them. We haven't seen a lot of them. Do you think there are still 4 more left on that assignment? Do you think you can handle those with no problem, or would you like to see 1 more?
1 more, please.
Okay. Which one would you like me to do? If we take a look at these problems, 2 is an that's an interesting one. Look, 5 we did, right? We did 5 yesterday.
Yeah.
6 has got 2 inductors. I don't think that one is that difficult, but certainly we can do that one. 4, I'd say 4 or maybe 2.
Go for 2.
Go for 2. Just get an interesting look for it. It looks tough, doesn't it?
Yeah.
I try to provide good hints for how to do these problems. So maybe I'll read my own hint and figure out what to do here. Okay, so this is a 2 inductor problem. We have 2 inductors here. So let's get all these values in. So this is IS. This is 1. This is 1. And then I have not a 4, I have a 2. And a 4 up the top. Okay. It says find the second order differential equation for the current. Write the form of the homogeneous response. The right-hand side of the equation should be a function of I of S. We know that. We know the right-hand side is a function of I of S. But I'm not telling you what IS is. This is for any source. I can tell you what IS is at the end. Hint, use mesh analysis and force one of your mesh currents to be equal to I. This is easy to force one of them to be equal to I. There's I right there. It's going to be easy to force it to be I. IS. That is I as long as I do this. I'll call that I1. Okay. So with that, let's go to work. There's nothing to do with IS. IS is a known source. That's awesome. There are only 2 equations. Loop I, loop I1. So let me try to put them on separate sides. Loop I over here, and then over here on this side. Loop I1. All right, for I. So we're in the direction of I, so it's going to L di dt, 1 times I minus IS prime. So we're looking for this voltage. That was this voltage right there in the direction of the mesh current. So the mesh current I is going in the clockwise direction. So it hits the positive side here, out the negative. So I need all the total current going up. Total current going up is I minus IS. I need the derivative of that. So I'm taking the derivative of that. That's why the derivative is on the outside. Okay, that's that term. Plus 4I plus twice I minus I1 equals 0. It felt a lot like the standard mesh equations that we wrote. Okay, a little cleanup on this equation, just a little bit. So I have, first of all, remember this is I prime minus IS prime. Now plus 4I plus 2I plus 6I minus 2I1 equals 0. Again, I want you to note that I have my I prime, I have my I over here, so it looks like differential equation for I. I'm almost there on that one, but it's not going to work. And I'm going to show you why it doesn't work, just to make sure we understand that. Okay, so now for loop I1, this is a pretty easy loop. It's going to be twice times I1 minus I plus 1 I1 prime. Clean this one up, and I end up with I1 prime plus 2I1 minus 2I equals 0. Okay, so the reason we can't use this equation to get our differential equation for I by just substituting in I1 is over here, I don't have an I1. I have I1, but it's in terms of I1's derivative. I want I1 just in terms of I, if I'm going to be able to substitute that way. So here's what we're going to do. This equation, I have I1 just in terms of I and the source, of course. That's all. That's a given. So what we're going to do is we're going to take this equation here, and we're going to solve this for I1. And we're going to substitute for I1 over there and for I1 prime over there. Let's do that. So if I take this, bring it to the other side of the equation, first I have 2I1 equals I prime plus 6I minus IS prime. I'm going to leave that like that because I have a 2I1 over here. You see that 2I1 that I'm circling? So I'm just going to substitute all of this into that. But now I need I1 prime. So the first thing I have to do is I have to divide by 2 to get I1 and then take a derivative. So I1 prime equals 1/2 I double prime plus 3I prime minus 1/2 I S double prime. So I'm taking a derivative of every term and I'm dividing every term by 2. And that I'm going to substitute in right there. Let's do that. I'll do that right down here. Not up there, we'll do it down here. So we have I1 double prime. I'll rewrite it. I1 prime plus 2I1 minus 2I equals 0. Here we go. Substituting in 1/2 I double prime plus 6I minus IS prime. That's that term. Plus twice I1. Twice I1. Whoops, I've got twice I1 already up there. I'll just replace twice I1. I prime plus 6I minus IS prime plus 3I prime. 3I prime, and that where did I get minus 3I prime? This minus 2I. I don't know where I got 3I prime. Oh, I'm looking at the line above it. I'm looking at this line above it. I want this one right here. Minus 2I. Minus 2I. equals 0. Okay. So I've substituted in, and now I'm going to clean it up. So here comes the cleanup. So first, 1/2 I double prime. Got that one. My I prime terms, I have just this one here. Did I copy this correctly? No, there's two terms, right? There's a prime here. Yes. Hold on. What did I do? I1 prime. I didn't even copy this down correctly, you guys. Let me clean this up. Minus 1/2 IS double prime. If I would just stare right here, this goes in to that. Okay, so my I prime terms, I have this one, and I have this one. So I have 6I prime plus 1I prime plus 7I prime. 7I prime. That's that one. That's that one. Now my I terms, I have this one and this one. 6I minus 2I. 6I minus 2I plus 4I. And then I'm going to take these other terms and bring them to the other side of the equation. Equals 1/2 IS double prime minus IS prime. We're almost there. We're almost scot-free. So we're looking for the differential equation. We multiply by 2, I double prime plus 14I prime plus 8I equals, multiply by 2, IS double prime minus 2 IS prime. So there's our differential equation. Write the form of the solution for the homogeneous response. Right? The right-hand side should be function. Write the form of the homogeneous response. So the homogeneous response, S squared plus 14S plus 8 equals 0. No quick factors that I know of that are going to get me the 14. So let's go ahead and use the quadratic formula. This might be a little ugly, but certainly you can help me out with numbers if I need some help with numbers. So S1, 2 equals minus B plus and minus the square root of B squared, 14 squared, minus 4 times 8, minus 4 times 8, all divided by 2. Okay, so 14 times 14, 14 squared is 196. We're going to take that 196 and we're going to subtract 32 from that, and that's going to give us 164. So this is minus 14 plus and minus the square root of 164 divided by 2. You can see that those are both real numbers. We're in category number 1. It looks ugly, but we're in category number 1. If we look at 164, we know that we can factor a 4 out of that. So this is equal to minus 14 plus or minus 2 root 41 divided by 2. I don't think we can reduce that anymore, except for this 2 part. That's minus 7 plus or minus the square root of 41. I know they're ugly numbers, but I want you to note one thing. First thing is a quick check for me. This came from a real circuit. I would expect that both of these numbers better be negative, and they are. One's close to 0. If that was the square root of 49, that would give me minus 7 plus close to 7, but it's not. So it's still negative. They're both negative numbers. Here is the form of the homogeneous response. I homogeneous is equal to K1 e to the minus 7 plus square root of 41 t plus K2 e to the minus 7 minus the square root of 41 times t. That is the form of the homogeneous response. Okay, not too bad. Not too bad at all. So you've got 3 of them that you're left with solving for. I've given you hints on each of them in terms of how to come up with this solution. So I think that you'll find that, yeah, they're a little challenging, but they're not too bad. Okay, we're moving to chapter 9. Chapter 9 is what is called sinusoidal steady-state response. So we've had steady-state response. We've seen that terminology before. What did that terminology mean to us before? And what were we able to do because of that? We've used that terminology, the steady-state response. What did it mean?
We could use the steady state model to replace capacitors and inductors.
Excellent. In this case here, in the sinusoidal steady state, it doesn't mean that. So here's really what the steady state means, because remember, that was when we had those first order circuits and all of the sources were DC, so we could put in the DC model. Well, we're in the world of second, and now we're going to go into third and fourth and fifth order circuits. Doesn't matter to us. So to be the steady state response, here's what we really mean by steady state response. So when we say we're looking at the steady state response, it means the homogeneous response has died out. And there's only the forced response left. Some forced responses can die out, but this last example that we did with the sinusoid, it wasn't the one that we just did, well, not this one because we didn't have a source in there, but this one with the sinusoid. See, this had a sinusoidal source. And I know that you don't quite understand this yet, but the sinusoid is the single most important function to us in electrical engineering. It's how we generate electricity. Everything is done to sinusoid. If you look at the current or the voltage that comes out of your socket in your wall, it is sinusoidal with a frequency of 60 hertz. So sinusoids are really important. So when we talk about sinusoidal steady-state response, the response that's left is the sinusoid. And we cannot put in a model that says, oh, the inductors are short circuits, the capacitors are open circuits. We can't say that. But what we can do is we can do some other very clever things. So just remember, when we talk about the sinusoidal steady-state response, we're not getting the homogeneous response. Is anybody going to lose any sleep about that? Oh my God, we don't get the homogeneous response. Why are we not losing any sleep over that? Tell me why we're not losing any sleep over that. Because in general, the homogeneous response is fill in the blanks. Homogeneous response is what?
Equal to 0.
Yeah, in general, it's equal to 0. It's gone after a very short period of time. It's equal to 0. So we're not going to lose any sleep over it. It only hung around for milliseconds. We want the response that hangs around forever. And that's what we're going to get here, the sinusoidal steady-state response. Okay? So that, in the world of sinusoidal inputs, so we are considering circuits that only have sinusoidal inputs. So everything we're doing right now, all of your sources are going to be cosines or sines. Okay? So only considering that. Now, we're going to put some variations here because we always do. But if we look at circuits like that, therefore, we know unless we have excitation at a natural frequency, unless we have excitation, let me write that, unless we have excitation at a natural frequency, so we know x of f, we're going to guess, is always going to be a cosine of omega t, whatever omega is, plus b sine of omega t. And we're going to find omega by looking at the sources that are in the circuit. That's where omega comes from. It comes from those. I just want to remind you, through mathematical manipulation, x of f is equal to square root a squared plus b squared. We're not going to write it this way. I just want you to know that this one here, square root of a squared plus b squared, cosine of omega t minus the tan inverse of b over a. I will remind you with this tan inverse of b over a, careful of the quadrant. That still matters. Careful of the quadrant. So what do I really want to show you? It really looks like this. It has an amplitude, so I'll just call it A sub m right now, a magnitude or an amplitude, cosine of omega t, in this case, minus, could be plus, theta a. It has an amplitude and phase angle. And this is what I want you to understand. We're dealing with circuits, and we put a sinusoid into a circuit as an input. Everywhere in that circuit, you're going to get out a sinusoid. If you put in a cosine, it doesn't matter because we know sines and cosines are related to each other. But if you put in a cosine, you get out a cosine. You put in this frequency, you get out the same frequency, but it's going to shift in its angle, and its amplitude is going to change. So you might put in something like the following. You might put in something that looks like this. Okay? And you're going to get out something, depending upon where you look, it might be smaller. Okay, so it might be shifted and might be smaller. Like that, it's going to be the same exact frequency, and it's going to be shifted by a certain amount. So it has a phase shift to it, and it has an amplitude scaling. That is what's going to happen for every current and every voltage in the circuit. That's pretty cool. Once we know that that happens, we can develop shortcut methods for solving these circuits rather than doing the differential equations. You saw how much math was involved in the differential equations when we had sinusoids, and it wasn't pretty. Let's first prove that statement up here. Let's prove that this, in fact, this is equal. So what is it I want to prove? Let's prove that A cosine of omega t plus B sine of omega t is equal to the square root of A squared plus B squared cosine of omega t minus the tan inverse of B over A. So this is a lovely identity. It pops up a lot in circuit theory. It pops up a lot in communication theory. So we see these a lot to do with cosines are really, really, really important functions. For those of you who don't know how we send signals through the airwaves, we send those signals on cosines. That's how we do it. Okay, so I need you to recall. Recall means I know you don't remember this, so recall it. How do you like that? That the cosine of A minus B is equal to cosine of A, cosine of B, minus sine of A, sine of B. Actually, plus sine A, sine B. I changed the sign in my cosine. So a lot of people write this one, cosine of A plus B, and that's where the minus comes from. But I'm going to do this with cosine of A minus B. So the minus here gives me the plus over here. So it actually looks like this. A minus here or a plus gives me a plus or a minus like that over here. So I'm going to stick with the minus. We'll do this way, cosine of A minus B. Okay, now this is what I want you to do. I want you to consider the following. So we're just going to recall this equation here. Now consider the following triangle. If you want to, envision this, if it helps you, envision this as being on the Cartesian coordinate system. If that helps you, envision it that way. Here's an angle theta. I want this length here to be A. So this length is A. That length is B. This here, we know, is the hypotenuse. So right now, let me just call this R, for lack of something better, equals R. And we know that's nothing more than the square root of A squared plus B squared. Okay, nothing funky going on there. Everything that we've known already, no surprises. So let's hold that thought. And at the same time, let's observe the following. If I wanted the cosine of theta or the sine of theta, let's do the cosine of theta first. Let's look at that triangle and tell me what the cosine of theta is equal to. Well, certainly the cosine of theta is the adjacent side over the hypotenuse. It's A over R. So that's equal to A divided by the square root of A squared plus B squared. We know the sine of theta is the opposite over the hypotenuse, and that's going to be B over R. And so that's equal to B over the square root of A squared plus B squared. So I've got the values for both the sine and the cosine of theta. Okay? So now what? Well, what happens if we go back to this equation here? Okay? I want to look at that equation. And what I'm going to do is I'm going to substitute in there for my cosine of theta and my sine of theta. Okay, I'm going to substitute for my cosine of theta and my sine of theta. So here we go. So I'm going to copy this down. So I have cosine of A and B, but now here's what I'm going to change this to. I'm going to rewrite this. It's going to be exactly the same thing. Watch this. Cosine of A, I want A to be omega t. B, I want to be equal to theta. So that's equal to cosine of A is omega t, B is theta, cosine of theta, plus sine of A, that's omega t, sine of B is theta. Great. Now, let's look at, for this theta that I have described here in this triangle, I'm going to use that theta, and I have this information about the cosine and the sine of theta. So let's utilize that information. So we have cosine of omega t minus theta equals. Now I'm going to write this term first. Same thing here. Why? Because it's a constant. I want to get the constant out in front of the cosine. So cosine of theta is a over the square root of a squared plus b squared. Now multiplied by cosine of omega t. So I just inverted the order. And I'm going to do the same thing over here, plus b over the square root of a squared plus b squared, sine of theta. Oops, sorry, that was my sine of theta. Sine of omega t. Sine of omega t. So I've inverted. That's that one. That's that one. That's that one. That's that one. Okay. Now I'm going to take this equation and I'm going to multiply this equation on both sides by the square root of a squared plus b squared. Multiplying here is going to cancel out. So I'm multiplying times square root of a squared plus b squared. And it's going to cancel with this term in the denominator that we have right there. It's going to cancel with this term in the denominator. A cosine of omega t plus b sine of omega t, voila. Now you might be asking yourself the following question. Maybe you're saying, hey, look at this. Let me just rewrite it another way. R cosine omega t minus theta. That seems like it would have been a lot easier to work with in our differential equations. Seems like it would have been a lot easier than doing two terms, term one and term two, and taking all those derivatives and everything. But there's a reason why in our differential equations, we left it this way. And with the work going forward, we're going to want to leave it this way. Anybody have any guess as to what was easier about this than this? It's not obvious, and it's not easy to figure out. Any guesses about what might be easier? Hint. It has something to do with when t is equal to 0. What happens when t is equal to 0 up here on those two terms? When t is equal to 0, what happens?
The sine term disappears.
Yeah, sine term disappears. What about the cosine term?
It just becomes a.
Yeah, just an a. The cosine itself is 1. So look at down here. Darn it, when t is 0, we end up with cosine of theta. Actually, cosine of minus theta. But because the cosine is an even function, that's the cosine of theta. And man, that gets ugly. So we have r cosine of theta. Ugh. That's not so easy as a 0 and 1. The numbers are much uglier. So it's much easier to work with this form for the differential equation because we use the initial conditions to solve for our unknowns. That's why we do that. Okay. So this is what we're going to do. We're going to look at the form actually that looks more like this than anything that we've had before. Okay? So we need, in order to do some work here, we're going to need to recall some basic trig identities. So we must remember so if you don't remember them, get these in your notes or use those CRC tables. So here's one. We just used it. It was pretty cool. It was that a cosine of omega t plus b sine of omega t. Remember, a and b can be negative. That's why quadrant matters. Equals square root of a squared plus b squared cosine of omega t minus the tan inverse of B over A. And again, I'm going to write this again. Careful of quadrant. You should find it interesting that B is the coefficient of the sine. The sine we know for e to the j theta. The sine is the imaginary part, goes with the imaginary part, right? Sine is the imaginary part. So the B goes with the sine, the imaginary part. It's still the imaginary over the real, imaginary over the real. Keep saying that over and over again. Okay, so that's one of them. Here are some others, and I'm going to give you the conversion formulas. So that's 1, 2. Converting, we will need to be able to do this. A sine, like sine of omega t, to a cosine. Okay, so recall that to do that, sine of omega t, and there are many mistakes that are made here, the sine and the cosine are just shifted from each other by 90 degrees. If I shift the cosine by 90 degrees, I get a sine. If I shift the cosine to the right by 90 degrees. So this is cosine of omega t minus pi over 2. So that's one identity. If you like degrees, or cosine of omega t minus 90 degrees. So we need to know that. There are times that we're going to have sines and cosines, but we need them all to be one or the other. They either all need to be cosines or all need to be sines. So we'll need that formula. Going the other way around. So that's converting a sine to a cosine. How about if I convert a cosine to a sine? How do we do that? So I want cosine omega t on this side. And so what is it equal to if I convert that to a sine? It's equal to the sine of omega t plus pi over 2. Okay, again, if you like degrees, sine of omega t plus 90 degrees. You take the sine function and we shift the sine function, and just quick sketches over here. Sine starts like that. I know that's an ugly sine function, but it looks like that. I shift it this way by 90 degrees. A quarter of its cycle, half of the lump. If I shift it by 90 degrees this way, that's a plus shifting it this way. I get the cosine. So those two are really important. Then we need the equations. That was 3, 2 and 2, 2 and 2, 2 and 3. And then number 4. So number 4 is converting cosine of minus omega t to cosine of omega t. Okay, so that's going to be important to do. Well, the cosine is an even function. This one's awesome. Cosine of minus omega t is equal to the cosine of positive omega t. It doesn't matter if I go this way on the axis or this way on the axis, I get the same values. 5 is going to be doing that same thing with the sine. Sine is an odd function. Unfortunately, it's an odd function. It is not an even function. And so this time we have the sine of minus omega t is equal to minus the sine of omega t. Six and 7. Converting a phase shift of 180 degrees. Cosine of omega t plus or minus pi radians. And I just want to convert that to a cosine of omega t. Okay, what is that? Cosine of omega t plus or minus pi. If I shift by 90 degrees, I end up with negative the cosine of omega t. So when we have something, oftentimes we have this, but the number out front we need is a magnitude, and we want that magnitude to be equal to a positive number. And so when we have a negative, we don't like it there. So what we do is we bury that negative into a phase shift, and I can shift it either positive 180 degrees or minus 180 degrees. And then the last one, the sine. Converting sine of omega t plus or minus pi radians to sine of omega t. So when we're just converting that one has the same thing. So this is sine of omega t plus or minus pi radians is equal to minus the sine of omega t. So sine and cosine do the same thing. When you shift them by 180 degrees, they change their SIG and sign. They change their sign. Okay, those are basics. We're going to need those. That's a good setup for us, and we'll refer back to those from time to time. So we're stepping into a world of what are called phasors. And phasors are really interesting. And so we're going to show you what a phasor is, and then I'm going to describe in words what it is, and I'm not sure how far we'll get today, but let's start with the following. Recall, e to the j theta is equal to cosine of theta plus j sine of theta. So we haven't seen that in a little while. Okay? Or if we put an r out in front, r e to the j theta is equal to r cosine of theta plus j r sine of theta. So it doesn't matter whether we have an r out in front or not. Okay? I want now for you to be thinking rather than theta, I want you to think in your mind, think of replacing theta, a fixed angle, of replacing theta by omega t. So now this becomes, when we look at e to the j omega t, the difference is this one changes its location with time. In fact, if we look at this, it is a complex exponential. First of all, its magnitude is 1, so this is the unit circle. Always critical to remember that. It's the unit circle. This is the real axis. This is the imaginary axis. And what this is doing is it's pointing to a particular location like here when t is 0, and then this thing is going around in a circle like this as t increases. That's what it's doing. It keeps going over the same circle over and over and over again. That is e to the j omega t. So it's not fixed in time, it is moving in time. That's the way I want you to think of this, okay? So as we look back here, let's look at now r e to the j omega t is equal to, r cosine of omega t plus j r sine of omega t. And all of a sudden I'm looking at terms that look like terms that come from a circuit. Note that r cosine of omega t is equal to the real part of r e to the j omega t. I just want you to note that. And at the same time, if it's worth noting, we tend to work with the real part, but also R sine of omega t is equal to the imaginary part of R e to the j omega t. So we can look at and focus our attention on this instead of this, or this instead of this. Now, you might be asking why we would want to focus our attention on that. Why would we want to do that? I want you to consider the following in our last 3 minutes that we have together. Consider the following voltage. Those are the kinds of voltages that we have in our circuit. Could be a voltage, it could be a current. Notice that this is the real part of V sub m e to the j omega t plus theta. It's the real part of that, which is equal to the real part of V sub m e to the j omega t e to the j theta. Oof, I love this. But that's equal to the real part of V sub m e to the j theta times e to the j omega t. Okay, I'm going to pause on this right now, and we're going to talk about this tomorrow, but I want you, before we part ways, to tell me, do you have any idea why I might have grouped that together? V sub m e to the j theta. Why did I group those terms? Any idea? I'm not asking you to tell me, I'm just asking, any idea why I might have done that?
Are they all constant?
Oh my God, who said that? Connor, was that you?
Yes.
Wow, it's all a constant. Now, it's not necessarily, and probably is not, a real constant, so I cannot pull it out of that real part function. I can't take it out of the real part. Okay, can't do that. But it's a constant. That's the part that's cool. So we have everything here in the V sub m e to the j theta is, all of that is a constant. And now the time varying part, which is where we have most of our hard work on our circuits, this is the time varying part. And if I can somehow figure out a way to use this, a constant times this exponential, you tell me what was easier in your circuits, in your differential equations, to have a cosine as the forcing term or to have an exponential as the forcing term? What was easier? I'll wait on anyone to answer that really hard question. In all of the work that we did, what's easier? Working with the exponentials in those differential equations or working with those darn cosines?
Exponentials.
Oh, you got it. It's those exponentials. So we put this in a form, and that's the beauty of sines and cosines. They're nothing more than exponentials. So we're looking at it in this form where, oh my gosh, I see this. I can treat it like it's an exponential, but over here, I've got to worry about this constant. This constant is the part that we're going to deal with, and we're going to say, hey, we know what the exponential is. Stop carrying it around. Stop bringing all of that with you in all of the work. We know we have a cosine there. We know we're going to get cosines. We have an exponential there. We know we're going to get exponentials. So let's just carry that term right there. And that's what phasors are about. Phasors are about us just carrying that complex term. I know it's complex, but it is a constant. V sub m times e to the j theta. which we will just use V sub m, the magnitude, theta as the phase shift of the cosine, and that's all we need to do. We don't need to carry the cosine around with us. We don't need to carry the omega around with us. We don't need to carry the t around with us. We'll just pop them back in at the end after we solve the problem. Now, solving the problem will require us to work with the complex number V sub m at an angle of theta. So the mathematics is complex mathematics. When I say complex, complex numbers. But all of the cosines, all of the differential equations, we're going to throw all of that out the door. We'll never have to use differential equations again when we do this phasor analysis for sinusoidal inputs. This only works for sinusoidal inputs. So that's the direction we're going. Any comments before we part ways for the day? Questions about that? I am trying as quickly as I can to get my notes to you and to get these lectures out on YouTube. For those of you who are using them and need them, I'm trying to get them out there as quickly as I can. So as soon as I'm done here, it'll take a couple of hours for the video to compile, and then a little bit of time after that for me to be able to get it up. But hopefully it should be up there by this evening for those who are looking for it, except for Jack. Jack, that'll be early morning for you. Please stay safe. The fact that we have shifted into more people working from at home tells us that there are tough days ahead. So continue to stay safe. Continue to distance yourself. This is serious stuff. Please be careful. Be smart about what you're doing. I'll see all of you. Have a good day off. Tomorrow, do some homework problems. I'll see all of you on Thursday. Rest of your day.